set our camera online so that we can see each other. Yep, that's better. Okay. Well, I guess most of you are tired, so that would explain your silence. If you have any issues, feel free to type in. So class, now that we have left the midterm behind us, it is time to distance ourselves and slowly leave the world of processes and enter the world of threads. Now, many of you have already used threads. You have used them very probably in the Java projects. I mean, those of you who have taken this course before, of course, they have used threads in various contexts. But for the remaining students that are witnessing these things for the first time, there are very few things that we need to talk about as far as threads are concerned. There are very few points that are important, especially concerning the differences between threads and processes, because there isn't really that much of a novelty. We are still in the world of concurrent programming. And this is just another tool that is available to us in order to implement concurrently, eş zamanlı, concurrently running programs. We already had the option to use multiple processes in order to have multiple workflows, multiple flows of instructions executed at the same time on a single CPU. Now we have one more option to exploit whenever we want to accomplish that. So threads, from a functionality point of view, işlevsellik açısından, they do not bring anything new to the table. It is just another option in order to implement concurrently running programs. However, in 99.9% of cases, so in almost all cases where you have a program that starts and runs on a single computer and then starts multiple flows of execution on a single computer, in almost all of these cases, you will see that the developers almost always choose option B, which is threads, and not multiple processes. And the reason for that is very simple. There are two reasons. We will be repeating them again and again within this lecture. There are two very simple reasons. The first reason is that threads are more efficient. In what respect? They are efficient in the sense that it costs less computationally in order to create them, as opposed to the creation of a new process by using fork. Fork is very powerful, but it is also computationally expensive. Why? Well, because you have to create all of those new data structures. I mean, we have already seen repeatedly how many data structures are associated with a single process. You need a table for the open files, a table for the memory segments. You need tables for signals. You need tables for etc. etc. You need tables. You need a lot of tables. So as soon as you make a copy of a process, you need to copy all of those tables. That costs a lot. Allocating new memory regions and so on. So fork is expensive. And especially consider the scenario where you have, for instance, a client-server paradigm. So many client processes connect to a single or make a request from a single server process. Now that server process, of course, is not going to respond directly to each client. It will create a worker, işçi, a worker process by forking itself. And that worker process will respond to the client. So if you have, for instance, many clients arriving every second, well, that means you have to create many worker processes every second in order to respond to each of those clients. And assuming that a fork is an expensive operation, I mean, you do not really have the luxury of creating tens of processes per second. I mean, you would need quite a significant piece of hardware in order to keep that sustainably running for a long time. So Reason number one, why we prefer threads over processes in order to implement concurrent programming is because they are more efficient. Efficient, why? In what respect? Efficient in terms of creation. They are efficient when it comes to creating additional threads. It is much faster and easier to create additional threads with respect to creating additional processes. Reason number two, main reason number two, why we prefer using threads over processes when we have concurrent programming issues on a single computer. And the reason number two is that it is easier to communicate. It is easier to communicate, to transfer data between multiple threads. Now, we have already seen how, well, let's not say hard, but impractical it is to transfer data between processes. You have to create a shared memory segment, maybe create a pipe, maybe create a FIFO. There are also message queues that we will not cover in these lectures. You have to create additional data structures, several system calls. Yes, I mean, it's not really that hard, but it's not easy, and it's definitely not practical. So the reason for that is very simple, is because processes cannot access directly each other's address spaces. However, with threads, as we will see later on, even if you have n threads, 10, 15, 50, 100, 1000, all running under the same process, under the roof of a single process, all of them share the same address space, the same heap, which means whenever one thread calls malloc and allocates a piece of memory, that address, the same address, is accessible by all the threads running under the same process. So as soon as you allocate some memory with malloc, it's the same thing as if you had allocated a shared memory segment. It's already accessible by all the threads. No need for anything extra, just the malloc, and that's it. So much more efficient, much easier with respect to creating a shared memory segment with all of the SHM opens and SHM close and SHM destroy and so on and so on. Just a malloc and a free, of course. Malloc and free, always together. Don't worry, don't forget. Now, they share the heap. They share global variables, static variables. They share the code, naturally, the same text segment. The only thing that they don't share is the stack. Each thread, as we will see, has a separate stack region, which means they have separate local variables. But all the rest are shared, communal variables, if you will, between all of the threads. Now, before we go any further, do you have any questions? Before we start, even. Soru soracak halde misiniz? Hocam onu sorsanız da diyeceksiniz. Evet. Okay. In that case, let's get on with our lecture. Now, threads, like processes, are a mechanism that permits an application to perform multiple tasks concurrently. Okay. A single process can contain multiple threads. Now, whenever we talk about threads, we are talking about threads that are under the roof of a single process. One process which contains multiple threads of execution. So one process, so if you execute the PS command, you will see a single process, but maybe it has 10 threads running in the same context of a single process. You don't know that. At least PS doesn't show you that. But they all appear as a single process. Okay. All threads are independently executing the same program, so the same exe file, the same binary file, and they all share the same global memory, heap, global, static, and so on, including the initialized data, uninitialized data, and heap segments. So basically, the only thing that they don't share is the stack. The threads in a process can execute concurrently on a multiprocessor system. So if by any chance you ever get multiple CPUs, multiple threads can in fact execute in parallel. So you can have one CPU executing one thread belonging to the same process, and another CPU executing another thread of the same process. That is possible, perfectly possible. In fact, if you have a CPU, well, one of the latest generation CPUs of the i7s and i9s Intels with hyper-threading technology, you can even have two threads executing in the same core. But that's an exotic scenario. I mean, that also assumes that you have an operating system that supports hyper-threading, etc., etc. Now, if one thread is blocked on input-output, the other threads are still capable, eligible to execute. So let's say that you have a process which contains two threads, and one of the threads tries to read from the hard disk. But for some reason, it is blocked. Maybe the file is empty. Maybe it is trying to read from a FIFO, and the FIFO is empty. Who knows? It is blocked. Does this mean that the entire process blocks? No. Only that thread is blocked, the one that called the read. The other threads running under the same process, they can still continue execution. It's beautiful. It's the same thing that we can accomplish with multiple processes, but with easier creation and easier communication. So why not use threads? That's the real question. Let's look at the memory. Now here we have a visual representation of the virtual memory address space of a single process, just one process. So we had seen something similar when we were studying the memory organization of one process. And the only difference with respect to that representation and this one is that here we have multiple stacks separated from each other for each thread. So if you have 1, 2, 3 threads, as you can see, we have separate stacks from them. So that means the local variables declared in each thread are in fact independent from the other. So one thread cannot access the local variables of the other. Well, from a compilation point of view, the compiler will not allow you to access them. But if you know the address, the actual address of a variable in the stack of another thread, there is nobody stopping you from accessing that address, since we are in the same address space, even though it is a very bad idea. Mr. Yusuf, a question.
So is it more likely to get Stack Overflow with multi-threaded applications because they are using separate stacks, a lot of stacks?
Well, it depends on how risky movements you make. But let me put it this way: not a Stack Overflow, but a stack-based error in memory accessing. Yes, it is very easy in this case. It is very easy. As it says also here, as it can be seen from the figure of the per thread stacks, they reside in the same virtual address space. This means that given a suitable pointer, so if you have by any chance the address, the pointer of a variable in the stack of another thread, you can actually access it. This is occasionally useful. I mean, I cannot really think of a context where it can be useful, but anyhow, but it requires very careful programming to handle the dependency that results from the fact that the local variable remains valid only for the lifetime of the stack frame in which it resides. So while this thread is accessing, while thread A is accessing through a pointer the local variable of thread B, how do you know that thread B is still alive? I mean, if thread B has already terminated, or if that stack frame at least has disappeared, then who knows what you're accessing? So it is very difficult to synchronize. And I really do not recommend taking this direction. If you want to share variables between threads, my personal opinion is to use the heap, basically. Just use the heap. Or you can also use global variables if you want to, if you already know the size of the variables beforehand. Do not try to use the stack for communication between threads. It's very risky, and it doesn't really present any concrete advantages. So please don't use the stack when communicating between threads. Use the heap, use global variables. Why not? But always keep the heap as a first option. So just like when you were using shared memory segments between processes, it is much safer in that regard. Now, are all of these threads executing the same code? No, not necessarily. Not necessarily. How does it work exactly? Well, I have a very nice figure of that in the upcoming slides. We will look at that there. For now, let's take a look at fork. Now, what are the advantages? Well, here we have some more details on the advantages that I have just told you. So threads offer advantages over processes in certain applications. Two big advantages. It is difficult to share information between processes, so communication. Since the parent and child don't share memory, we must use some form of inter-process communication in order to exchange information between processes. So this is a problem with fork. Threads don't have that. Process creation with fork is relatively expensive. They need to duplicate various process attributes such as page tables and file descriptor tables, means that a fork call is very time consuming. Whereas with threads, we have solved those two problems. Well, relatively speaking. Sharing information between threads is easy and fast. It is just a matter of copying data into shared, either global or heap variables. But of course, in order to avoid the problems that can occur when multiple threads try to update the same information, we must employ some synchronization techniques. So just because now we no longer have a shared memory segment, but it is the memory segment that we're using is by default shared, I mean, we are in the same memory space, the same heap, the same global variables. This doesn't mean that we no longer need to synchronize access. Race conditions, so two threads attempting to access the same variable at the same time or the same data structure at the same time, that still exists. We still have that problem. Communication, yes, solved very easily. Just declare an array or data structure on the heap. But synchronization, no, that problem is not solved. That is up to us. So we still need techniques in order to address the issues of synchronization, just like when we were dealing with processes. However, at least now, it is much faster to create new threads, since we no longer have to copy, duplicate multiple tables. And what about synchronization? We will not talk about synchronization in this lecture. We will talk about it next week. Now, of course, you can still use the techniques available from processes, so semaphores, pipes, and FIFOs, and et cetera, but with threads, we have something better. We have condition variables, and we have mutexes, which are sufficient in order to solve all of your synchronization problems. So once you start working with threads, you no longer really need semaphores anymore. You just need mutexes and condition variables. And of course, the monitors, condition variables and mutexes together. We will get to that. Now, how exactly does it work with threads? Now, on the left, we have a standard function call. So you have the calling program on the left, which calls the function process fd. Okay, but you have a single flow of execution. Tek bir program akışı var. It starts from the top. As soon as it calls the process, as soon as it calls the function, the workflow, the execution flow continues inside that function. And when the function naturally returns, we return to the calling program and the flow continues from the calling program. We have a single thread of execution. Burada tek bir iş parçacığı var, tek bir akış var. A, B, C, D, N, Z'ye kadar gidiyor arkadaş. Arada başka fonksiyonların içinden geçebilir. That's normal. Hatta o fonksiyon başka fonksiyon da çağırabilir. Bugüne kadar böyle yaptık. Up until today, this is what we did. Now, when you have multiple threads, this is what happens, the one on the right. So the calling program, the initial program, the one that you started when executing the program, when the process started its lifetime, when it calls pthread create, P is short for POSIX. So POSIX thread create, what it does is you give it a function as a parameter. And when that function returns, look, I'm not saying a system call, I'm saying a function. These are library functions. And when the function pthread create returns, it continues execution from where it was, the calling program. But from that point on, you have an additional execution flow. And what is that executional flow executing? Now with fork, it executes exactly the same things as in the parent process. With threads, it executes the function that you gave it as a parameter. Çok önemli bir fark. When we called fork, we duplicate a process. And when fork returns, we have two processes, and both of them continue from the point right after fork. With threads, it is different. When you create a new thread, you are specifically telling the pthread create function which function to execute in a separate execution flow. Yani net olarak ona söylüyorsun. Arkadaş bak, yeni bir iş parçacığı yarat ve o iş parçacığında şu fonksiyonu çalıştır. Başka şeyleri değil. Net olarak şu fonksiyonu, adını veriyorum. Şu fonksiyonu çalıştır. Yani fork'a göre çok daha rahatız bu konuda. Hani abuk subuk if else'lere ihtiyacımız yok yani. Yok işte bunun process ID'si şuydu, else böyleyse yok şunu çalıştır falan filan. Gerek yok artık. When a new thread is created, it runs concurrently with the creating process. When creating a thread, of course, you indicate which function the thread should execute. Now, this is nice. This is good news for us. This makes it easier for us to control who is executing what. This is nice. This is good. A function that is used as a thread must have a special format. Now, this, of course, doesn't mean that you can give just any function to pthread create in order to execute as a separate thread. It must conform to certain minor limitations. Now, the function to execute as a separate thread takes a single parameter, just one, not two, not zero, one parameter. Well, it can be zero if you set it to null, of course. It takes a single parameter of type pointer to void. So void star, and it will return a pointer to a void. Now, this doesn't mean that we can only pass a single parameter. I mean, that single parameter can be a struct, and we can put into the struct end fields. So in practice, basically, we can pass as many parameters as we want to. So that is not really a limitation. It's just a matter of format, really. The process fd function that we saw in the previous example might have, for instance, this prototype. So void star parameter, void star return type. Let's look at an example. So at the top, you can enlarge it in your own screens. That's why I am not zooming in right now. So here we have, for instance, what? Oh, here we have the process fd function. So this is the function to be executed as a separate thread. So let's look at it. Of course, it returns void star. Yes, the parameter is of type void star. Well, it has a local character buffer. It converts the parameter first into an integer pointer, and then it retrieves the integer value from that address. And then it simply reads from that file. It doesn't matter what it does, basically. What matters is that this function that we will give to pthread create will be executed in parallel to the original thread of execution. We still have one process, but we have multiple threads of execution in parallel. On one side, we are executing the main function in the main thread. By main thread, I mean the thread that existed initially when the process started. And we have an additional thread that will execute process fd in parallel. Now, let's look at how we start that new thread. Well, basically, we simply call pthread create. We give it the name of the function to execute as a separate thread. And we additionally have some parameters. Now, what are these parameters? Now, the last one is the parameter to pass to the function that will be executed as a separate thread. The first one, TID, is just a variable that is supposed to hold the identifier of the thread. So this is the variable that will contain the numerical identifier of a thread. It's something similar to a process ID, so that we can tell apart the different threads. Threadleri birbirinden ayırt edebilmek için sadece bir kimlik numarası. The second parameter, which is null in this case, and we will see it later on, is basically the parameter that we use in order to pass some arguments to the thread creation phase. Thread oluşturma aşamasına bir iki parametre vermek istiyorsak onları da bu ikinci parametreyle veriyoruz. Onun da örneklerini göreceğiz. So this is just to give you an idea of what it looks like. Managing threads. Now, don't worry, we will look at pthread create in detail in the upcoming slides. For now, we are just looking at the general principles. Now, who manages the threads? Now, I said that these are functions, pthread create, etc. So this means these are library functions. So these are not system calls. So that means it's not the operating system that is managing this stuff. So who is managing the threads? Who is creating threads? Who is stopping threads? Who is scheduling threads? Who decides when a thread must stop temporarily and another thread will be executed in its place? Who does that? So let's look at that part step by step, because things are a bit complicated, as you will see, because there is not a single type of a thread when it comes to scheduling. There are the user threads, there are the kernel threads, and there are the hybrid threads. Now, things might get a bit complicated at first. Don't worry about it. Read your textbooks and your operating system textbooks afterwards in order to clarify things. But please do not worry about it if you cannot figure out exactly what is happening between hybrid threads and user threads and kernel threads, because what is very important for us as the individuals who actually develop the programs is that it doesn't matter to us. It doesn't really matter how exactly those things work behind the curtains, because it will not change the way in which we will develop them. So maybe the library is using hybrid threads, maybe the library is using user threads. We are still going to write the same program. So don't worry about it. But please do your best in order to understand the differences between them. Now, a thread package usually includes functions, of course, for thread creation and thread destruction, scheduling, enforcement of mutual exclusion, conditional waiting, and so on. So for synchronization issues, creation, stopping, and so on. The standard functions that you would need from a thread library. Now, on your systems, if you're using a flavor of Linux, you will have the POSIX thread library already installed. Now, when compiling your programs, you will need to add it to the linking stage with LP threads. Just like whenever you use math functions, you include the LM flag to the linker. So if you use the pthread functions, pthread create, mutex, waiting, stopping, in any way, you need to include the POSIX library during the compilation phase. You can find more details online about that. It's very easy. You just add an additional flag and that's it. Tire LP threads and you're done. Now, a typical thread package, such as POSIX threads, also contains a runtime system to manage threads transparently. By transparently, we mean that the user, so us basically, is not aware of the runtime system. So we are not aware which thread is executing when. Now, when a thread is created, the runtime system allocates data structures to hold, of course, the thread IDs, the stack, program counter values. So imagine that you are developing such a library on your own. So you are developing a library that will manage threads. So what kind of things do you need in order to make it transparent to the user? Well, obviously, you will need data structures to store the identity numbers. You will need some kind of a mechanism to decide when to execute which thread. You will need to keep count. You will need to take into account where each thread is in the program, in the function that it is executing. One thread might be at the beginning of the function. The other thread might be executing another function and might be at the end of it. So you need to keep track of who is executing what and when they should be executing it. So the scheduling phase. And of course, you also need to provide mechanisms for the synchronization. All of those things are provided by the POSIX threads library. Now, thread management. Now, I'm not going to get into the full details of how the POSIX threads library works. I'm just trying to give you the main idea of how it approaches those problems. Now, when a thread allocates space for a return value, so let's say that that thread executed a function concurrently, it finished it, and now it has to return a value. Now, some other thread is responsible for freeing that space. A thread which has its own stack, run, executed, finished. Now it has some return value that needs to be returned, but the thread has already finished. So somebody else, of course, will need to clean up after that. Just like when a process terminated, the parent process needs to clean up after the child. The child cannot clean up after itself because it has already terminated. The same problem also exists here. Now, of course, for the other resources that you might allocate during the execution of a thread, so you might be running a function inside the thread, and you might allocate additional memory. You might open some files. Now, just like when you are handling processes, at the end of that thread, it is expected from you, from me, from us to free those resources before the thread terminates. Herkes kendi kapısının önünü temizlemekle yükümlü arkadaşlar. So every thread cleans up after itself, but not of course the return value that we cannot clean up. It is the, well, there are many options on that. We will get to that. So long story short, if you allocate resources during the execution of a thread, make sure that you free them before the thread ends, just like with processes. When creating multiple threads, do not reuse the variable holding a thread's parameter until you are sure that the thread has finished accessing the parameter. Now, here by parameter, it in fact references this right here. So basically the variable that we are passing to the thread's function. And basically it tells us that if you intend to create multiple threads, 2, 3, 4, 10, 50, 100, make sure that you have distinct variables, different variables that you pass to each of those threads, because you can never be sure when a past thread, a thread that you started in the past, has finished reading that variable. Buraya kadar soru var mı arkadaşlar? Any questions? Şu anda çok yeni şeylere girdik çünkü. Mr. Alp says, since threads share data on the heap, doesn't cleaning up mean losing allocated data for other running threads? Mr. Alp, if the allocated memory region is something that you have allocated with the intent to share with the other threads, yes, that would mean deallocating it, freeing it, while the other threads are still trying to access it. That would mean destruction. That would mean messing up the entire synchronization. What I'm talking about is the case when either you have allocated some space only for that thread, which means it is safe to deallocate it once the thread is finishing, or maybe you have indeed allocated it for common use, but you are sure that nobody else is using it anymore. So by means of some kind of synchronization. But most of the time, this is just a parenthesis, whatever communication oriented, so whatever shared memory allocations you intend to make, we usually make that in the main thread even before starting the threads. So that way, we are certain that only one thread has created it, so we no longer have to worry whether we are the first thread creating it or not. So that is one more plus point for threads. In the main thread, you just create you just call malloc and you allocate that region of memory, and then you can pass that pointer to all the threads that you want to create. And so they can use it. And at the end of those threads, either one of those threads, the one that is executing last, can free it, or the main thread, after all of those threads have terminated, the main thread can free it, being sure that all of the threads that used it are now done. So both options are okay. Wow, today we only have 19 students. Okay. So in that case, I should make sure to have a nice recording for the others in case they watch it. Okay. Thread safety. Another new concept. Now you remember we were talking about signal safety in the past. Now we are going to talk about thread safety. What is thread safety? What is there to be unsafe about threads? Very simple idea. Now, it is not difficult. to create new threads. In fact, it's very easy to create threads. You just call pthread create, give it a function, and it starts executing in parallel. The problem is when these threads that are executing these functions, that can be the same functions or different functions, altını çiziyorum. Bir sürecin altındaki iş parçacıkları aynı fonksiyonu çalıştırmak zorunda değiller. Hepsi farklı birer fonksiyon çalıştırabilir. O konuda hiçbir kısıt yok. I'm trying to underline this. All the threads under a single process, they can run each of them a separate function in their own thread. They don't have to run the same function repeatedly, all of them concurrently. They can run different functions. If you have n threads besides the main thread, you can have n different functions executing parallel. That's okay. That's perfectly normal. Or you can make them all execute the same function concurrently. That's up to us, whatever you want to do. However, sooner or later, some of these functions will call existing C library functions. Now, what you need to pay attention to at this point, when you call C library functions, is that some C library functions are coined, bir betimleme var onların man sayfalarında. There is a certain expression in their man pages for certain C library functions saying that they are thread safe, which means that it is safe to call that C library function from multiple threads at the same time. It's okay. It will behave as it is supposed to behave. For example, you want to count how many times a certain character appears in a string. That's okay. You can call the same function from multiple threads concurrently. Or can we? Let's check. Hop, mesele değil. So is this thread safe? Or is it? Does it say anything about thread safety? No, it says nothing about thread safety. So should we assume that it is thread safe? Never assume anything. So we should be checking deeper into the man pages right now. What happens if it doesn't say that a certain function is thread safe? Well, you can assume in that case that it is thread unsafe. Or if it says explicitly that it is thread unsafe, then that means there is no guarantee that it will behave as it is supposed to behave when you call it at the same time from multiple threads. Why? Well, maybe because it is using a certain global variable inside it. You don't know the contents of that function that you have just called, the C library function. So if it is using a global data structure, so that means when you have multiple threads calling the same C library function, well, in that case, maybe they will end up modifying that common data structure in erroneous ways, in mistaken ways, and you will destroy that data structure. So basically, a thread unsafe function, C library function, means that they have not taken any precautions against concurrent access. Eğer bir C kütüphanesi fonksiyonu, herhangi biri, printf, scanf, fark etmez, herhangi biri için thread safe değildir ifadesini görüyorsanız, valla bu durumda arkadaşlar bu demektir ki birden fazla iş parçacı eş zamanlı olarak onu çağırdığında o fonksiyonun ne yapacağının hiç sağ solu belli değil. O yüzden çok dikkatli olmak lazım. Dikkatli olmaktan kastettiğim nedir? Önlemini alıyorsun ki o fonksiyonu belli bir anda ancak bir tane iş parçacı çağırsın. So let's say that there is a C library function that you know that is thread unsafe, but you still want to call it from multiple threads. What do? Well, you take precautions. You use mutexes, you create a critical section, and you make sure that at a given time, only one thread calls that C library function. If you know that it is thread safe, no worries, no mutexes, no nothing, just call it like a normal function. Mr. Yusuf says, are all system calls thread safe? As far as I know, no. You have to check the man page of each of them. But I'm not sure about that. But as far as I know, no, they shouldn't be thread safe, all of them. I think there were some exceptions, but C library functions, most of them are thread unsafe. C library functions, no system calls, C library functions, most of them are thread unsafe. So be very careful. So you might get some weird results when you're calling C library functions for multiple threads. So do not be alarmed. If you get weird results, that means you have to check the man pages. And if you see that it is not thread safe, make sure that only one thread is calling that function at any given time. So, okay. Another interaction problem occurs when threads access the same data. Now, in more complicated applications, a thread may not exit after completing its assigned task. Instead, the worker thread may request additional tasks or share information. Now, basically, this means that the most simplest case that you can have is a thread that just simply starts executing a single function. And when the function is over, well, the thread is over. But in some cases, you can have, for instance, infinite loops. For instance, I'm sure that you have all heard about thread pools, iş parçacığı havuzları. Now, in thread pools, for instance, when a program starts, it starts by creating n threads. Daha baştan da hiç iş falan yok. It starts by creating, you have the main thread, but it additionally creates n threads, n being a certain parameter, 10, 20, 50, 100. And all of those threads, they wait for a certain task. And whenever the server receives, the main thread receives a task through a socket, through a FIFO, through some other means, it gives that task to one of the threads that is available. Once that thread completes the task, now it goes to the beginning in its loop and waits for another task. So you can't have threads running infinitely in an infinite loop like this. Thread pools are very commonly used in the web servers, database servers, and systems that receive many requests per second. It's a very effective way in order to handle them. Okay. Now, this brings us now to the distinction between user threads and kernel threads. And before going any further, let's take a last question before taking our break. Mr. Anil says, how do we know the functions we wrote are thread safe? Well, Mr. Anil, just ask yourself this question. You have written a function, and just imagine it, try to visualize it, that you have two processes or two threads or 10 threads calling it simultaneously. And try to see what it would break inside that function. If there is something that would break, well, that means it is thread unsafe. It's as simple as that. I mean, there is no black or white control button that you can push to tell you whether it is thread safe or unsafe. Since you are the person that wrote that function, it is up to you to evaluate, to determine whether it is thread safe or unsafe. And as I said, just try to imagine it, that you have multiple threads or multiple processes executing at the same time. Now, most of the time, the problems appear due to global variables used inside that thread, and especially if it accesses static variables. So you can have multiple functions, the same function, executing at the same time, accessing the same static variable. That is a recipe for disaster. If you have a static variable inside it, very probably that function is not thread safe. But generally speaking, maybe you have some data structure inside it. You have pushes and pops inside it. So maybe one thread is calling the push statement, executing the push statement in the same function, and another thread is executing the pop statement in the same function. And they are both manipulating the same stack. And so we can have the same problem that we had when we were dealing with the lecture on semaphores. So if we have a common data structure that can be shared across the calls to the same function, if you have static variables, global data structures, very probably it will be thread unsafe. Okay, so class, it's 9:19. We will stop for 10 minutes and we will continue at 9:29.